When someone mentions NASA, what comes to mind? Astronauts on the moon? The space station? Rovers on Mars? The Voyagers now flying through interstellar space. But there's no place NASA has explored more than our own planet. NASA has a fleet of satellites that are constantly collecting data to monitor the health of the Earth. Using the vantage point of space to understand our planet dates back to the beginnings of the space age. It was then, in response to the Soviet Union's Sputnik, that JPL built and helped launch the first US satellite, Explorer-1. Inside Explorer was this science instrument, a kind of Geiger counter designed to detect cosmic rays. It also discovered the presence of radiation surrounding the Earth, what turned out to be a belt of charged particles held in place by Earth's magnetic field. They are named the Van Allen radiation belts for the scientist who built Explorer's Geiger counter. This was the very first science discovery made from space. A major finding about our planet. For these belts shield the Earth, deflecting solar particles that would otherwise shred our atmosphere, over time destroying it and everything about our planet as we know it to be.
More than half a century has passed since the time of Explorer-1. And today, we know that our planet is changing in ways we need to understand. I'm Mike Meacham, a systems engineer here at JPL. The job of a systems engineer is to look at the big picture of how all different parts of a spacecraft are supposed to interact as one system, and to make sure that they do. The Earth is a system too, with many parts. The land, the ice caps, the oceans, the atmosphere, and living things. I want to discover, along with you, how Earth's complex climate is changing. In the next hour, we are going to explore the role JPL has and is today playing as part of NASA's larger effort to understand what's happening to our atmosphere. But to begin, let's start our journey by visiting the planet known as Earth's twin.
Five, 4, 3, 2, 1, 0.
The year is 1962, and we're on our way to Venus on board JPL's Mariner 2 spacecraft. Venus was the first planet chosen to explore for a very practical reason. It is our nearest planetary neighbor. And that proximity offered the best chance for success in the early days of the space age. Still, Mariner 2 barely made it there. At the time of the mission, JPL produced this film, which explored how Venus had once been thought of as Earth's twin, given its smaller size, density, and cloudy atmosphere.
Where does the story start? Historically, I suppose it began more than 100 years ago, when man first viewed the clouds of Venus. Because of the thick clouds, it seemed logical to suppose Venus...
There had even been speculation that beneath the planet's clouds, there might exist a tropical world of jungles, swamps, and rainforests. But by the time of Mariner 2, a radically different view of Venus was emerging, due in part to the research of a young scientist who was beginning to make a name for himself, Carl Sagan.
Many theories of the Venus environment have been suggested. However, new information eliminates at least some of these theories. Measurements with radio telescopes show that there is a region on Venus where temperatures are greater than 600 degrees Fahrenheit. It is just possible that the hot region exists at a high altitude. However, it is more likely that the hot region is the surface, heated either by an enormous greenhouse effect or by wind friction. Therefore, if there is life on Venus, it is probably of a type that we cannot now imagine.
Tantalizing, exasperating Venus. A single significant experiment can confirm old or create new theories.
Mariner 2 and the missions that followed did just that, turning Venus into the poster child for global warming. Earth's twin? More like Earth's evil twin. That label was further reinforced when JPL's Magellan spacecraft used radar to penetrate through the clouds and first saw the surface of Venus, a tortured landscape full of ancient volcanoes, more than any other planet in the solar system. Some may still be active. But 1 billion years ago, Venus may have had an Earth-like climate with oceans of water. Yet over time, something went catastrophically wrong. Volcanoes may have played a role in creating this hellscape that is today's Venus. But the primary cause may be the result of the sun's solar wind. Charged particles that are constantly streaming off our star. The effect of this endless bombardment of radiation weakened Venus's magnetic field, making it unstable and leaving the planet to fend for itself. It may be as simple as Venus wasn't able to handle all this heat. As temperatures rose, the oceans evaporated, turning into water vapor. Then carbon dioxide also built up in the atmosphere, resulting in a runaway greenhouse effect.
With Venus being a little bit closer to the sun, basically meant that it never really had a chance. So over time, that carbon dioxide and water vapor built up. It was impossible for any water to stay on the surface as a liquid. It all stayed in the atmosphere. That produced a massive greenhouse atmosphere that produced a tremendous amount of warming, probably warming even greater than what we're seeing today with surface temperatures around 950 Fahrenheit.
Our next closest planetary neighbor is Mars. Like Venus, the red planet shares similar features with Earth. Mars has polar caps, seasons, and a rotational rate nearly identical to our planet. But any hopes that Mars might have been more Earth-like were squashed after the first flyby of the planet by JPL's Mariner 4. A handful of grainy black and white images from the mission was all that was needed to see that Mars is a barren world. Just like Venus, scientists believe that ancient Mars was more like today's Earth. It was warmer and wetter, wet enough to have had oceans. But about 4 billion years ago, Mars lost its magnetic field that served as a planetary shield. And without the shield, the Martian atmosphere was, like Venus, left at the mercy of the sun's solar wind.
And as it cooled, the interior froze up. And when that happened, the dynamo that generated its magnetic field froze up as well. And that was the end of it for Mars.
It took about 500 million years, but eventually the solar wind shredded the Martian atmosphere. And as it disappeared, the exposed oceans evaporated. And the planet cooled down into the frozen world it is today.
So long ago, Mars and Venus were not just our nearest neighbors, they were our close cousins. Today, Mars is in deep freeze, and Venus is a furnace. Sobering examples of how a planet might flip from paradise to hell.
Are we just lucky that Earth resides in a Goldilocks zone where it's not too hot, not too cold, but just right? That's part of the explanation. But there's also the delicate and intricate balance of interactions taking place throughout our planet's system of water, ice, land, atmosphere, and all living things. The more we learn about these interactions, the more we are understanding how fragile the Earth is to change.
Our planet is warming, and the major causes of that are greenhouse gases like carbon dioxide, or CO2 for short. Carbon dioxide is a chemical compound comprised of 1 part carbon and 2 parts oxygen. The oxygen, not a problem. The carbon, everywhere you look, you're going to find it. It's the basic building block of life. It's in the animals, the fish, the plant, the trees, and in me and you.
Nature has an elegant but simple way of using carbon. It travels from the atmosphere into organisms in the Earth, and then back into the atmosphere over and over again. This process is called the carbon cycle. It has helped to keep our climate in balance for at least the last 100,000 years, if not millions. As part of this cycle, carbon from decaying organisms can end up in the ground, where it can be transformed into coal, oil, and natural gas, which we started using as fuels to power machines over 200 years ago. And that changed the natural order of things, as more and more carbon in the form of CO2 is ending up in the atmosphere, where it soaks up and re-emits heat. Have you ever wondered why carbon dioxide and other gases are called greenhouse gases? It's an analogy, of course. A greenhouse works by letting in light, which heats up objects inside a structure like this, keeping plants warm. But if light can get in through this glass, why can't the heat escape back out? The answer is that light and heat are not the same. The light that we see coming off the sun is just a sliver of the electromagnetic spectrum. Energy that ranges from very long wavelength, like radio waves, to shorter wavelengths, like X-rays. The wavelength that we can pick up with our eyes is a relatively shorter wavelength of radiation that can penetrate through this glass. Heat, in the form of infrared radiation, has longer wavelengths, and it can't travel through the glass as easily. The result? The greenhouse warms up. CO2 in the atmosphere works in a similar way. It slows the heat escaping out into space. And the result? The Earth warms up. Across the globe, humans output about 40 billion tons of CO2 into the atmosphere every year. But let's turn that number into something more down to earth. Let's say the average car weighs about 2 tons. So we, the world, by burning fossil fuels in various ways, are putting the equivalent mass of 20 billion cars into the atmosphere every year. And the lifetime of CO2 in the atmosphere, hundreds of years. With nearly every passing year, the level of CO2 is rising. In 1950, the record for the highest amount of CO2 that had stood for 800,000 years was shattered. Since then, the spike has soared. And now the Earth is heating up at the fastest rate of any known time in the history of our planet. The last time CO2 was this high was nearly 4 million years ago. A time when sea level was 78 feet higher than today, and the Arctic was covered with forests. The importance of CO2 and other greenhouse gases was not lost on scientists at JPL. One of them was Mustafa Shaheen, a native of Lebanon who moved to the United States to attend college. In 1958, while pursuing his PhD at UC Berkeley, he saw in the news the iconic image of JPL's Explorer 1 being held aloft. That moment inspired him to pursue a space career, which took him to JPL. Moose, as everyone called him, was as non-assuming as he was brilliant. He served as JPL's chief scientist, and it was largely his idea to create an organization to harbor and nurture the lab's growing number of scientists.
For outstanding performance and leadership in developing the JPL Earth and Space Sciences Division and enhancing the science programs of JPL and NASA. Mustafa T. Shaheen.
Moose's motto was, "Always make progress." And for 3 decades, Moose was fixated on finding a way to study Earth's atmosphere from the vantage of space.
The value of satellite data is that it gives you global coverage. Now we can get global coverage with the same accuracy as balloon-borne instrument.
Moose's ambition was to build a science instrument that would help to understand climate change. But that proved to be a hard sell politically. So he stressed how the same instrument could also be used to improve weather forecasting.
The mission is to understand the relationship between weather and climate. For example, are the weather anomalies, which we are seeing today, hurricanes, etc., are they related to climate change?
And for that idea, he found takers. Moose's instrument, called the Atmospheric Infrared Sounder, or AIRS, was one of 6 science instruments that won a spot to fly aboard NASA's Aqua satellite.
3, 2, 1.
AIRS was designed to detect infrared energy over a range of more than 2,000 wavelength bands. And from those bands, it was hoped, for AIRS was officially an experiment, that it would be possible to create 3D maps of atmospheric temperatures and water vapor. But before any of these measurements could be put to work, all of the raw data of zeros and ones first had to be calibrated and validated.
Once you have those numbers that you think represent reality, you have to confirm that they are reality. And this is one thing I did for the first 5 or so years of the mission, pretty much daily, including a lot of weekends. Just looked at what air said and what, say, a weather balloon said. Or what air said and what an aircraft that flew underneath air said. And with several years of hard work, we concluded we weren't crazy, that the numbers that we reported from the instrument were actually representative of reality.
And soon, AIRS began delivering on its promise. Its measurements were helping to improve weather forecasts.
That was said to be enough to pay for the instrument itself. So forecast really was a major accomplishment. But NASA's not a forecast center.
And Moose, always trying to make progress, next wanted to explore how AIRS might be put to use to better understand climate change.
As part of AIR's original purpose of improving weather forecasting, the instrument had already gathered a wealth of data about water vapor, which is H2O in the form of an invisible gas. We know it best as humidity.
Water vapor is also a greenhouse gas. And there's more water vapor than all other greenhouse gases combined. But through the ages, the warmth provided by water vapor has been a good thing. Without it, our planet would be just a frozen ice cube. Water vapor is part of nature's normal recycling of water from the Earth's surface into the atmosphere, and then back again to the surface. And this recycling goes on constantly, but on different timescales. A piece of ice in the Arctic can remain a solid for millions of years. A drop of water in the ocean, thousands of years. That same drop of water, in the form of water vapor in the atmosphere, on average, just 9 days. The amount of water vapor in the atmosphere is directly related to temperature. The warmer it is, the more water evaporates, becoming water vapor. And more water vapor results in warmer temperatures.
So you've got here a cycle. When you change the state of water from vapor to liquid, this change releases enormous amount of energy into the atmosphere. The understanding it is critical to understanding our climate change. This is why it is important.
At any one time, the atmosphere contains over 37 million billion gallons of water vapor, which contains an astonishing amount of energy. And all this water vapor doesn't disappear into thin air. It is constantly transforming back into water, ice, and snow, which rains down on us, often in the form of storms that are becoming more frequent and more severe. But water vapor is not the driver of global warming. The main catalyst is carbon dioxide, CO2. And Moose wanted to tease out of the air's data the signature of CO2 and other greenhouse gases, which he nicknamed the culprit. But detecting CO2 from the data proved an enormously difficult task, what his team likened to unscrambling a scrambled egg.
So the problem here is looking at a set of data with the information you want, but the noise is so high that what you are looking for is within the noise. The unscrambling of a scrambled egg. That difficulty was thought of as unsurmountable.
But just 4 years after the launch of AIRS, the insurmountable was surmounted. The culprit, Moose declared, had been coaxed out of hiding.
We've done it. Now we are looking at climate.
This is the first global map showing the distribution of carbon dioxide around the world as seen from Earth orbit. It clearly shows a distinct pattern of high carbon dioxide in the northern hemisphere, which was consistent with predictions made by climate modelers. Methane, another greenhouse gas, is seen here having a global distribution similar to that of CO2. Here, carbon monoxide, which is not a greenhouse gas, can be seen being created by the burning of forests in the Amazon. The gas then makes its way across the Atlantic. Fires in Africa can also be seen. This animation is composed of nearly 6 years of AIRS' first observations. The overlaying of the up and down curves are CO2 measurements made from the ground that correspond to the seasons. It is a way of showing how the Earth breathes. Note the steady march of CO2 upwards. The map continues to be updated, all showing a constant increase of CO2. 20 years after being launched, the AIRS instrument on board NASA's Aqua satellite is still operating, eyeing from Earth orbit not only greenhouse gases, but hurricanes, dust storms, wildfires, volcanoes, and of course, helping weather forecasts. It was a kind of progress Moose had always hoped to accomplish.
It is like having worked for an idea. And I had doubts, my colleagues had doubt, but 30 years later, the idea works. And this is the great sense of happiness, of satisfaction I get and my colleagues get out of AIRS, you know. that a concept that we worked on for 30 years worked, and worked very well. This is great.
The pioneering success of AIRS helped to create a pathway for CO2 hunters that followed. Here at JPL, a handful of scientists plotted out a new mission, the Orbiting Carbon Observatory, or OCO. It was envisioned as an instrument to fly on a spacecraft devoted solely to measuring carbon dioxide.
The goal was to learn where CO2 was being created, what are known as sources, and where it was being absorbed, sinks. It was already understood that half of the CO2 was being absorbed into the atmosphere, leaving the other half going into sinks in the oceans, forests, and the land. Exactly where and how much were unknown, but OCO intended to find the answers, adding a new dimension of data on top of what AIRS was providing.
AIRS measures CO2 at high altitudes in the atmosphere, about halfway between where we're sitting on the ground here and where airplanes fly. And so it was a useful measurement for studying the impact of carbon dioxide on greenhouse effects, but it wasn't useful for actually tracking the sources that were emitting carbon dioxide into the air and the natural sinks that are absorbing it at the surface. For that, we needed to use reflected sunlight rather than thermal energy to make this measurement, and we can essentially count all of the molecules from the top of the atmosphere down to the surface and back to space. That measurement's much, much better for tracking CO2 sources and sinks.
In 2002, the mission was given the go-ahead by NASA. By then, scientists everywhere were realizing that climate change wasn't something far off in the future. It was going to impact their children's lives, if not their own, which made the work of the OCO team even more urgent.
The original Orbiting Carbon Observatory mission was a long, difficult project. It took 9 years of effort, 1,000 work years, a lot of trials and tribulations to get to the launch site. So on February 24th, 2009, we were finally there.
Step 130, verify all estimates armed to stage 0. Copy, check 130 complete. Check 131, RCLC, send range status, alert signal, and verify.
It was indeed a beautiful evening. You can clearly see the stars in the sky. There was very little wind. So it was a perfect night. The air was just filled with excitement.
RCLC, step 132.
So we went through the manuals and made all our final checks, and I gave the go-ahead, saying that, yeah, OCO is ready to launch. And I remember the countdown being given, 10, 9, 8,
7, 6, 5, 4,
3, 2, 1,
0. Liftoff of the Taurus rocket with OCO, tracking a greenhouse gas in seek of clues to global warming.
All of your senses are heightened, your emotions are running on overdrive. All of those years' work is finally leading up to this culmination. We could hear the rumble, inside of the control room.
DVC is nominal, attitude nominal.
We're not just glued to our chairs, but also glued to the monitors.
0 TVA initialized, pressure nominal. Expecting stage 1 ignition in approximately 5 seconds.
It was a beautiful launch.
Vent cover jettison. Stage 0 burnout, stage 1 ignition, stage 0 separation. Vehicle attitude nominal, power bus is nominal. Stage 1 burn will last approximately 70 seconds.
You couldn't have asked for anything better.
Because the sky was so clear, we could actually see the rocket go all the way to the horizon, just with our naked eyes, and we got some beautiful pictures of that. Everything went perfectly. up until 3 minutes and 50 seconds after the launch.
Bearing separation. Vehicle attitude nominal following jettison of payload fairing. Proper load shedding.
We were listening intently on our headsets, and then I heard some chatter.
Approximately 130 miles. Vehicle is... What was that?
But I was also looking at the screen. The animation was still showing everything was fine, but my eyes were telling me one thing, but I was hearing something different.
I was in the control center, standing at the screen, watching the numbers go by, and I knew that to make orbit, I had to go 7 kilometers per second. And every calculation I could do in my mind at 2 o'clock in the morning was telling me those numbers weren't adding up. So I turned around to the main engineer for the rocket, and I kind of went like this, and he goes, "I'm sorry."
I'm Ned. It appears we've had a contingency with the OCO mission. Please enact the mission mishap preparedness and contingency plan. Begin with notification, data impoundment, and mishap response tasks. Do not leave your station. Do not attempt to call out and release information to anyone or speculate on the cause of the contingency.
It was devastating. Everything seemed so surreal. We kept looking at this plume from the second stage, and we're hearing all this chatter on the engineering net, and it just didn't make sense. It was just this sense of disbelief and shock.
NASA's Orbiting Carbon Observatory satellite failed to reach orbit after its 1:55 and 31-second launch time liftoff from Vandenberg Air Force Base.
It only took a few hours to determine what had happened.
Preliminary indications are that the fairing on the Taurus XL launch vehicle failed to separate. The fairing is a clamshell structure that encapsulates the satellite as it travels through the atmosphere.
The fairing, the pointy end on the rocket, was supposed to open up. That didn't happen. The mechanism that was supposed to open the fairing failed, malfunctioned. And so the fairing stayed on the rocket.
Instead of reaching orbit, the spacecraft, still encased in the fairing, re-entered the atmosphere and fell back to Earth.
It was like losing somebody you've loved. It was that emotional for all of us. But I would say 24 hours later, those emotions turned into a resolve.
But along with resolve, to refly the mission required new funding.
This was not an easy time to try to go back and refly a mission that you had just lost. We had just dropped $250 million in the Indian Ocean. We were going to go to Congress and the White House and say, "Can I have some more money to do it again?" This is hard to do at any time, but it was especially hard to do in February of 2009, because we were in the depths of the greatest recession since the Great Depression.
It took a year to get the NASA funds to rebuild the mission, which was named OCO-2. But the funding ended up being delayed. Keeping the team intact while marking time became a new challenge.
7, 6.
Then NASA suffered the loss of another spacecraft. The Goddard Space Flight Center's Glory mission, like OCO, was launched from the same launch site on the same type of rocket.
We were at T plus 300 seconds. The vehicle speed error is indicating underperformance.
And met the same fate for the same reason.
Which is expected due to a fairing not separating.
The loss of glory caused further delays for the launch of OCO-2.
Do not leave your stations until release. Do not attempt to call out and release information to anyone or speculate on the cause.
Years passed before the cause of the glory and OCO fairing failures was tracked down. But in 2019, the U.S. Department of Justice announced that a manufacturer whose materials had been used in the fairing release mechanism had agreed to a fine of $46 million to resolve criminal charges and civil claims related to falsifying test certifications. Five years after the loss of the first OCO spacecraft, the second orbiting Carbon Observatory was sitting on the launch pad.
330,000 pounds. At T-minus 1 hour, 38 minutes, 8 seconds and counting, this is Delta Launch Control.
We knew we had built an OCO-2 that was going to work, and I felt a lot of excitement. It was a beautiful launch, but it was the one that we didn't see.
On this night, Vandenberg Air Force Base was fogged in. Not that anyone really cared, for OCO-2 would be treated to a perfect ride.
2, engine started. 0, liftoff of the Delta II rocket with OCO-2, tracking a greenhouse gas in seek of clues to climate change.
So I remember one of my colleagues saying, "Hey, wow, that was one of the best launches I never saw."
Good chamber pressure in the 3 solids, good symmetrical burn. 22 seconds in, still looking good. Good chamber pressure on the second stage. Standing by for fairing jettison. And we have fairing jettison. Standing by for SECO-1, standing by. And we have SECO.
I mentioned to a lot of you that we wanted an opportunity to finally complete some unfinished business, with the loss of the original OCO mission, and we've taken the first step in that direction. Solar arrays did deploy, and we are power positive.
And now OCO-2 was circling the Earth 14.5 times every day, and completing a full mapping of the Earth every 16 days, making millions of individual measurements that now had to be translated into usable data. But OCO-2's challenges were not over. After calibrating the instrument, scientists thought something was wrong.
There was a problem when we recognized that the light signals of the glint data over the ocean were not nearly what we thought they should be. On the land, that data was looking really good. But when you look over the ocean, you're looking at where the bright sun glint is. We were starting to analyze that data. The retrievals weren't looking good. And then one of our guys had plotted this as a function of the angle of the sun. And he says, there's a certain pattern I expect I'm going to see, and I'm not seeing that pattern. I know this idea is kind of crazy, but this data sort of looks to me like you're measuring with the wrong sensitivity to polarization. And just to clarify what polarization is, we probably all have a pair of sunglasses. And if you have polarized sunglasses, when you look at a piece of water, right, it's not super glary. And if you turn your sunglasses 90 degrees, you would actually see the glary light again. So it's very different at this 90 degrees off, especially over water reflections. So he's like, I think we've got our sunglasses on sideways. We're looking at the wrong polarization. And we're like, are you serious, Chris? We're both like, are you serious? And we're like, uh-oh.
The problem was traced back to an error in the design of the science instrument, a flaw that could not be fixed with a spacecraft in orbit.
This is where the engineering team again saved our bacon, and they found that, in fact, we could just fly our spacecraft a little bit angled. It was not such an angle that the sunlight wasn't enough, so the solar panel still got enough light. It wasn't 90 degrees to get that full sensitivity, but it was a third of the way there, and it actually increased the signal enough. In the end, right, I can make it all sound like, oh, simple solution, rotate your spacecraft. There was a lot of angst between, I think our sensitivity is different, and here we go with our little rotated spacecraft. But yeah, wow, that was quite a start of a mission.
Then a new problem arose. Following the loss of the Glory mission, OCO2's launch was delayed for more than a year, forcing the spacecraft to be put into storage. And that had unforeseen consequences.
While we were in storage, unknown to us, the focal planes, the detectors that detect the light, the infrared light, were slowly pulling themselves apart because they were at room temperature and they wanted to be really, really cold, halfway between room temperature and absolute zero. And so when we flew the mission, many of the detector pixels across our infrared focal planes had gone bad. So it's just another challenge. We still had plenty of pixels that worked. The question is, how do we work around the ones that went bad? We calibrated a whole set of data, we ran it through computers. It took months and months of processing, and the products that came out weren't good.
The scientists were forced to scrub through their data a second time. And remember, OCO2 was beaming back about 1 million individual measurements, or soundings as they are called, every single day. That's 24 soundings a second. And most of them, like those taken at night over clouds and those bad pixels, are of no use. They have to be filtered out. So by the end of every day, the team has about 85,000 usable soundings. Yet even with a really fast computer, it takes about 5 minutes of computation time per sounding to derive any useful information. And to do this, thousands of computers have to be lashed together. And the CO2 that scientists are seeking to find in the data is absolutely minuscule, about 400 parts per million. Which means detecting 400 CO2 molecules residing in the midst of 1 million other molecules. It's enough to bring even a supercomputer to its knees. It all points to the fact that we're now in a different space age. Coping with these massive data sets is now as much or more of a challenge as creating the rockets and science instruments that are now being flown. And to the dismay of the OCO2 team, their measurements still weren't adding up.
So there was an early version of our OCO2 data that we don't even like to talk about amongst our team. A math calculation got put in the wrong order, and the subset of data we were testing with this error was not obvious. But once we gave it to the data processing team and they started running through a year of data, you built up a time series and you could really see, oh, something is not right in this data set. You don't imagine some of these things that could be happening, and so you'd not imagined it, you didn't test for it, and you didn't see it, and there you go. It shows up, and then you're like, oh, completely missed that one. In hindsight, I've gone through this process so many times over, I'm like, oh, that's par for the course. But it was my first time with delivering a big data set, being one of the key responsible members, and I was just like, holy cow, I can't believe we did that.
The team, which had been working 24-hour days, regrouped, came up with a different solution, and that solution worked extremely well. And then we were able to reprocess that data to derive CO2 values that have basically led the world in precision and accuracy.
But surprises with the OCO's data results, what scientists call end products, kept on coming. The biggest of them came from Mother Earth herself.
By the spring of 2015, just as we're starting to get a useful product out of it, we started realizing the product was not looking quite like what we expected. We expected a product that would show us that tropical rainforests were the lungs of the planet, and we expected them to be where the CO2 was being pulled out of the atmosphere by those marvelous trees and plants all the way across the tropics. We weren't seeing that. We saw that the Amazon is actually emitting carbon dioxide into the air, not absorbing it.
The Amazon, the largest rainforest in the world, has been known to be a major absorber of CO2. So what had caused such a profound shift?
Thought, oh my gosh, biomass burning, fires, wildfires are burning in the tropics, and that's adding carbon dioxide to the air. And that turned out being a tiny piece of what was actually happening.
What else was happening was an intense El Niño, a climate pattern that causes an unusual warming of waters in the Pacific. And this El Niño was also warming the Amazon.
They had been going through years of drought. And the extra drought and heat associated with the El Niño just basically shut the trees down. They stopped photosynthesizing. They stopped even trying to grow. And because of that, they stopped absorbing carbon dioxide like they usually do. But that was just the Amazon. In Africa, they had plenty of rain. But it was incredibly hot, the hottest temperatures they had seen. Plants actually absorb carbon dioxide through photosynthesis, but they release carbon dioxide through respiration. And because of the higher temperatures, the respiration was outstripping the photosynthesis. Then we had Southeast Asia. And in Southeast Asia, Indonesia, it was fire. The fires were burning out of control. We got to watch all of this happen with OCO2 and make detailed measurements of how the land biosphere, these trees, were interacting with the atmosphere.
With all of these tropical forests emitting rather than absorbing CO2, it would seem that the amount of carbon dioxide in the atmosphere would skyrocket. But that had not happened. Instead, for some reason, CO2 was being absorbed someplace else. But where?
Well, it turns out that most of it looks like it's going into northern hemisphere forest. So the forest across Europe, across Asia, across North America. So we're still tracking that down because it's not going into those forests uniformly. Some of those forests are burning down. You hear about the giant fires across Alaska or across Siberia. That's emitting carbon dioxide, but yet the forests around them are growing. And why are they growing? Well, climate change. As the climate has become warmer, the growing seasons have become longer. The number of trees and the size of the trees has been increasing. So a lot of things are happening with climate change that are changing where the sinks are going. It could have been that when we originally wanted to launch OCO back in 2009, that the tropical forests actually were absorbing CO2. They're not now.
Scientists do not know how long the northern forests will be able to carry the burden of absorbing CO2. But we do know more about the health of forests, thanks to OCO2. That's because scientists have been able to tease out of the data the fluorescence of plants. This faint glowing, invisible to the naked eye, is a natural part of the healthy photosynthesis process. The kind of energy being emitted can tell us much about the condition of forests, plants, and even crops. This bonus science was one reason why a third OCO instrument was built out of leftover spare parts. But OCO3 is not a carbon copy of OCO2. Instead of flying on a spacecraft, it was designed to be installed on the International Space Station in 2019. OCO3 can be thought of as a kind of point-and-shoot camera, which gives scientists more flexibility in zeroing in on areas of interest. And among those targets are large cities. Urban areas account for more than 70% of all greenhouse emissions caused by humans. These are scenes of Los Angeles, which has the 5th largest urban carbon footprint in the world. It's one of the many urban areas around the globe that OCO3 has set its sights on. With a single pass over the Los Angeles basin, OCO3 can take snapshots that can reveal tiny differences in levels of CO2 throughout the area. The highest readings, in yellow on this map, are on the west side of downtown LA, a densely populated area with congested freeways and CO2-emitting industries. The amount of CO2 being emitted there is about twice the global average.
Los Angeles has an ambitious plan to become carbon neutral by the year 2050. That will be no easy task. But having the ability to track CO2 emissions from the ground, the air, and from space will be crucial in understanding the path forward, for there's a lot of unfinished business ahead of us.
We've not touched upon ozone yet. And here there's an encouraging story from the past that can help to guide how we choose to confront climate change in the days ahead. At the beginning of our journey, we saw that JPL's Explorer-1 mission discovered the Van Allen radiation belts that protect our planet from harmful solar radiation. And it turns out our planet has a second line of defense, the ozone layer in the upper atmosphere that acts as a sunscreen, blocking ultraviolet rays that would otherwise sterilize the Earth and damage all living things. But back in 1985, the surprising results of a British expedition to the Antarctic landed like a bombshell. The discovery of a dramatic drop in the amount of ozone gas at the southern pole, what came to be known as the ozone hole. This discovery raised all kinds of questions. Was the hole an aberration? Why was it only at the South Pole? Was it spreading? And if so, how long would it be before the hole reached populated areas? An urgent concern was knowing what was causing the ozone depletion. Theories abounded. Might there be a natural explanation? Or was it human-caused? The United States rushed a scientific expedition to the Antarctic the very next year. The team included JPL scientists who deployed on the ground a science instrument originally designed for high-altitude balloon observations. Their results, and those of other measurements made on the expedition, pointed to a human cause for the hole, a class of chemicals called chlorofluorocarbons, or CFCs, that were being used in everyday products like hairsprays and air conditioners. In the years that followed, many more types of ozone measurements were made, many of them by JPL teams who used balloons, aircraft, satellites, and the space shuttle as platforms for their instruments. Early on, many nations of the world, alarmed by the news that CFCs were destroying the ozone layer, quickly agreed to address the problem by signing the Montreal Protocol. This international agreement called for reducing CFC emissions by half and later called for a complete ban. It is the only UN treaty that has ever been ratified by every country on Earth. And today, the ozone hole is healing. Based on current projections, a half-century from now, ozone in the atmosphere will return to healthy levels once again.
What's being done to tackle ozone is a model, a roadmap for addressing the greenhouse gases that are warming up our planet. But make no mistake, this will be a much harder and longer road for the world to travel than ozone. Remember early on when we met that young scientist who shared his findings about what greenhouse gases had done to Venus? 2 decades later, in 1985, Carl Sagan would again address the impact of greenhouse gases, but this time it would be about our planet. His words are as true for us today as they were then.
We have a kind of handwriting on the wall. The power of human beings to affect and control and change the environment is growing as our technology grows. And at present time, we clearly have reached the stage where we are capable, both intentionally and inadvertently, to make significant changes in the global climate and in the global ecosystem. Because the effects occupy more than a human generation, there is a tendency to say that they are not our problem. Of course, then they are nobody's problem. We are passing on extremely grave problems for our children, when the time to solve the problems, if they can be solved at all, is now. It is also a global problem. The nations, to deal with this problem, have to make a change from their traditional concern about themselves and not about the planet and the species. A change from the traditional short-term objectives to longer-term objectives. I think that what is essential for this problem is a global consciousness. A view that transcends our exclusive identifications with the generational and political groupings into which by accident we have been born. The solution to these problems requires a perspective that embraces the planet and the future, because we are all in this greenhouse together.
We are all on this planet together, and the path forward will take all of us working together. I'm Mike Meacham. Thanks for watching and for taking care of the good Earth.